Alrighty, so I wanted to talk about couple moments and how they differ from regular or moments caused by forces. And to do that, I wanted to do it through through an example problem. So let's bring that in. Okay, so in this one, we're asked if the couple moment produced by the forces acting on the beam on the left are the same as the couple moment produced acting by the forces on the beam on the right. Right, and so it is important to note that the forces here, we have a 6 kilonewton force here, and here, as well as here, and here. So I think it's important to let's just talk about, we'll come back to this actually. Let's talk about couple moments or another way sometimes people call these pure moments. Means the same thing. That is not. There we go. That looks better. Yeah, just the same thing, same meaning, different word. Versus, let's make it red. We're getting serious here. Versus, I'm going to call them normal or typical. Call them normal, typical. Could also call them singular force causing or cause or singular moments. So let's compare these two a little bit and actually figure out what's going on here. So actually let's draw a line and not do that. It's not straight at all. That's also not straight. There we go. And let's get rid of this. And I think that's going to annoy everyone if, there we go. So, couple moments, they cause rotation. So, we know that, right? Both of these cause a rotation. They actually cause not necessarily rotation, a tendency to rotate. Both of these do. Just to be clear, a tendency to rotate. And moments actually have the same units as torque. So you might have heard that a car has something like 1,500 foot-pounds or 1,500 Newton meters of torque. That's just a measure of essentially how much rotational power the engine has. So that's just an example from real life. It's mostly typically used with car engines. I can't really think of any other examples where the statistics are commonly used. You see it a lot in Formula One races actually. There's a lot of torque. You need a lot of rotational power in order to actually um, to change the tires. You also need a lot of torque to lift the actual Formula One car off the ground. If you see a pit stop, you'll see that there are two people, one at the front, one on the back of the car, that use jacks to actually lift up the car so that the other mechanics can change the tires. Um, they're exploiting torque to do that, or moments, same thing. Okay, so some differences though. Let's actually stay with white. So both of these have a tendency to rotate. Couple moments are caused by two equal and opposite forces. Whereas these singular moments, the reason why I called them a singular moment is because they are caused by one force. And when I mean one force, you can have multiple forces that all add together to create one force. But I'm just thinking of the simplest example where if we have something like this, and we have a force going down, right? That's just a single force. And if we have a couple moment, we're going to have one force here and one force here. They're going to be equal and opposite. So hopefully that makes sense. Let's get rid of that stuff and this guy. Okay. And the reason why I wrote down here this pure moment, this is why they're actually called pure moments, is because they cause rotation only. Because rotation only anywhere and anywhere on the body. That's why that sometimes you can see a couple moments they're drawn. Sometimes they're drawn. Let's go yellow. Sometimes they're drawn just like that or like that. That means that if I have, let's move down a little bit. If I have sort of a beam here, again, just keeping things very simple. And I have a couple moment, and let's just say that this is the one I'm interested in. That couple moment could be acting here, it could be acting here, here. It doesn't matter. I can put it anywhere I want, and they will all produce the same magnitude of rotation, right? And that should make sense. If I have a couple moment with a magnitude of 200, say 200 Newton meters, that's going to be 200 Newton meters, no matter where I place it. So it could be here, 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 here. Wherever I place the couple moment, its magnitude is going to be 200 Newton meters. Okay? So it's going to cause rotation no matter where I place it. Okay, moving over here. Actually, let's go back. There we go. The magnitude of the moment in a sort of a singular moment is dependent. I'm pretty sure that's how you spell it. Could be wrong though. It's dependent on both the force and the distance. And distance. Okay. So another way that we can think about this is, let's go back to my beam example again. So if I have a force, and let's say that I'm concerned, let's call this point A here that we're interested in. Let's call this F1. So that distance, that is not, let's go from there to there, let's call that D. If F1 is the same, and if I can pull this off, this will be very cool. There we go. If I just take F1 and not put it there, come on. If I take F1 and I slide it to somewhere else, and I keep F1 the same, right? Let's say I put it about right here. So it's about that new distance from here to here. It's about D over 2 now. My moment's going to decrease, right? Because it's a force times the distance. And conversely, if I move F1 back over, and I increase it, so let's say that instead of F1, I just make that magnitude a lot bigger. And instead of F1, I have F2. That's going to cause a larger moment. So the important thing here is that the rotation is dependent on two things. It's dependent on the force, but assuming that I keep the force the same, it's dependent on where I place the force in my system. And so unlike the couple moment, which we saw where if I have a magnitude of something like 200 Newton meters, I can place it anywhere, right? It doesn't matter where I put it, it's the tendency to rotate is going to be the same. This is not the case for a singular moment, right? The magnitude is going to change. The magnitude of the moment is going to change depending on where I place the force, right? So it's distance and also the magnitude of the force. Okay. So there we go. So now let's look at the problem that we have. See if we can apply our new found knowledge to this problem. I'm going to move it over a little bit just so we have the most amount of space, and Microsoft doesn't seem to want to let me do that. So thanks, Microsoft. Okay, so we're just going to place it here. Actually, no, we're going to go over here. Okay. So let's think about this again. So is the couple moment produced acting on the beam the same as the left as the couple moment acting on the right? Okay, so two things to notice. I'm actually going to blow this up a little bit if I can. Will it let me? Maybe not. No, but I can zoom in, so let's zoom in on it. Haha, I've outsmarted you. Okay. So we know a couple things that we can see right off the bat. The distance, or sorry, not the distance. The forces are the same, right? 6 kilonewtons here, here on the one on the left, and 6 kilonewtons here and here for the one on the right. So that's good. We know that the forces are equal. And so now the only thing that's left is the distance, right? Because the angles don't necessarily matter. That's something that's really interesting here, is that you probably see this coming in at angles and you're like, oh no, the angles that this is coming in with and that these two are coming in with are different, so then I'm going to need to use like sine and cosine and everything's going to get all crazy, and then next thing I know I'm going to be asked to calculate the distance to the sun, and then I'm going to have to rederive quantum mechanics. No. You need to focus on the absolute basics of what this question is asking, which is, it's just asking about the couple moment. Do I not have a pen? Give me a pen, please. Thank you. It's asking about the couple moment, and so all we know, couple moment, is just going to be the force times the perpendicular distance, right? All that's going to do is produce a tendency to rotate. So all we're looking for is the force and the distance. The force and the distance. So when are they going to be the same? Well, what if d1, this distance here, was larger than d2, right? Let's say that this is not 5 because we said it was larger. Let's say that this is 6, and let's say that this is 5. Well, then the couple moment here would be 6 times 6, and it would be 30. And this would be 6 times, this would be 36. Let's write that out. And this would be 30 kilonewton meters. So this would obviously be larger. So what if we made them the same? Let's try that. Let's make this guy 6. No, we'll do the math right this time. 6 times 6 is going to give us 36 kilonewton meters, which matches the one over here. So notice that even though these forces here and here are coming in at an angle, whereas these are not, and they're also sort of elevated on these pedestals, whereas these two definitely are not, their tendency to rotate is the same as long as their perpendicular distance is the same. The angles don't matter here, which is something that might seem sort of counterintuitive. Hopefully it makes a little bit more sense now, because all we care about is the mutual perpendicular distance between the two forces. As long as the forces are equal and opposite, we don't care what angle they are coming in. That's why this is true, essentially. That's why the math works out. So hopefully that makes more sense.